Because I wrote
Oh, I'm chair.
Yeah, it's not.
Can you see now? I basically I tried to pronounce J, but I shouldn't pronounce it.
it's a Stanojkovski.
You're going to butcher it.
I'm going to butcher it. But that's not good for it. Mima likes me, so I get away with butchering her last name. We'll wait for that clock. No, thank you. That's fine, you may indeed. Okay, good afternoon everybody. Welcome back to the second session of today. Very pleased to have Mima Stanojkovski Frenkel to talk to us about groups and elliptic curves.
Thank you very much, Eamon, and I want to start by thanking the organizers, first of all, for inviting me to be here and to give me the chance to speak. I must confess, it is my first time here, so unlike the first two speakers, it is really my first time here. So I won't be talking about something that happened in the previous edition, and I will be talking mostly about joint work with Joshua Maglione. I want to clarify something about my title. So it says groups from elliptic curves. Well, elliptic curves are projective varieties that have a structure, an additional structure of an abelian group, but those are not the groups I want to talk about. I want to build P groups from elliptic curves, and I will leverage later in some way on the group structure of the elliptic curve, but we'll get there. All right, so just for the setting, oh sorry, I learned that I have to point there. Just for the setting, what I really focus on is, I want to understand what happens if we build groups, how many can we build, P groups mostly, and how can we compare them, right? So if we want to classify groups, we have two questions we want to answer, or better, two tasks that we have to perform. First construct them and then compare them up to isomorphism. And the most difficult task is telling isomorphism, telling two groups apart by isomorphism. And I like to think of two families of groups as sort of like the two at the end of one spectrum and at the end of the other. So we have simple groups on one side constituting finite groups. But thanks to the classification, we know we can do polynomial testing for isomorphism for finite simple groups. On the other side, if we think of finite groups as composed by P groups through CELO theory, then we can ask, well, how hard is it in that scenario to perform isomorphism? And those are the groups that are the main obstruction to knowing whether isomorphism can be performed in polynomial time. And this is just for the setting. And if we want to speak of the most general complexity when we deal with finite groups, we're not very far off from doing brute force. But if we focus on P groups, there are more specific algorithms that aim to tackle this question. And so we have work of Ike, Linden, Green, and O'Brien that tests isomorphism relying on something called characteristic structures. This can be characteristic subgroups, but also other types of characteristic structures. For instance, you'll see in my talk the characteristic structures are really these elliptic curves. And I do look forward to the talk of James that I think will be telling us about finding characteristic subgroups without using automorphisms. This is happening on Thursday, if I'm not wrong. We do know we can do polynomial time testing for abelian groups.
Sorry, how do you present your groups when you give them to the algorithm?
You can just give a presentation.
Presentation?
Yeah. Yeah.
Probably not.
No?
You don't mean a finite presentation. You probably mean a power conjugate presentation.
Yes.
Like that.
Yes. I mean, yes. In this case, yes. For the P groups, yes. Thank you. And but as soon as we move away from abelian groups, then things get complicated. To the extent that even if we go class 2 and we clear all the p powers, so we work with exponent p, we already don't know whether we can perform isomorphism testing in polynomial time in general. But we do know that we can do it if the commutator subgroup is small, up to order p squared. Okay, thanks to work of Brooks, Peng, Maglione, and Wilson. And here I'm not giving credit to many of the people that worked on isomorphism testing recently and produced very good algorithms. I just want to focus on what we know we can do in polynomial time. So up to, let's say here, d equal at most 2. So this is the number of generators of the, the exponent of the size of the commutator subgroup. We can do it, but it's open for d at least 3. And this is what I will focus on today. So my commutator subgroups will be small, and I will, in the end, focus on d equal to 3, though I will say something on also some other cases. All right, so one thing that we can also do, so I told you, we started with the question of classifying finite groups. We said we construct them and we test them up to isomorphism. Maybe we cannot provide a full list, but we can also ask, like, can we at least count them, know how many there are? Okay, so in the case of P groups, we can count them, say, by order. Here, P to the n, so I call my function fpn, will be the number, will be the function counting the groups of order P to the n up to isomorphism. And we do have explicit formulas for exponent n up to 7. And this is the best that we can do. Okay, here I listed some of the names associated to the production proof of these formulas. I just want to point out that if you look at the paper of James, where he classifies the groups over P to the 6, there are some errors. So I want to point you to a preprint, recent preprint of Higman, O'Brien, and collaborator, where these mistakes are really pointed out, so that in case you run into that paper, be aware that there are some errors in there. And we also do know the asymptotics, this function. But this is as far as we go with these formulas in full generality. I mean, one thing that was conjectured in the 60s by Higman is a particular behavior of this counting function of the groups of order P to the n as soon as n is fixed. So I'm fixing the exponent n. And Higman conjectured that this function is polynomial on residue classes. Okay, so this means that we can, according to the congruence class of the prime modulo some integer n that depends on the exponent, we can describe this function in terms of polynomials. And this conjecture is still open, and it is confirmed by the values for which we know the actual value of the function. Okay, so there I put a little table that tells you, given the exponent, what the big N is. Okay. All right. So as I told you, this conjecture is still open, though relatively recently, there has been some questioning on whether it is really true. And I think the first instance of where an example was provided that might show that this is not true was given by Marcus de Satoy and Michael Fonley in 2012. And what was the example? Where they constructed a family of groups of order p to the 10 as central extensions of a sum group GP of order p to the 9. And this group was constructed as the FP points of a unipotent group scheme. I'll tell you in a second how to do this construction. But the point is that this family really is indexed over the primes. So you do have a definition for all the odd primes of this family. And then what they showed was that this family had a non-PORC counting function. And the reason why this family did not have a PORC counting function is that the function counting the automorphisms of this group, GP, is non-PORC. Okay, this is related to the P-group generation algorithm and how you count the orbits of the extensions that you take this particular type. So before I tell you more about this, let me just explain why they presented this as potential evidence against the PORC conjecture. Because this is one family of groups of order p to the 10. The reason why they said this might give a hint that it might not be true is that up to then, to prove that certain counting functions were PORC, what was done was to use the fact that adding PORC functions and multiplying them preserves PORCness. So quasi-polynomiality, other word for PORC. So then they said, well, this is one subfamily that is not PORC, so maybe we cannot add them up, all the contribution to a PORC function. Okay, but very soon, another example was constructed of a family of groups of order p to the 9 where a subfamily was identified with a non-PORC counting function. So this was sort of like the big fuss on this example got sort of lowered a bit thanks to this new example, and many more examples were constructed later. So I don't want to talk about these other examples, but I will be coming back to this one, because this was the first one that was constructed and somehow the only one of its kind. So at the beginning, some of us thought, well, how special is this example, right? And by the end of this talk, I hope to convince you that it's not special at all. But you have to really work to be able to say this. All right? So I promised you I was gonna define how you construct these groups, these FP points, this group GP from the previous slide. And before I do this, I wanna sort of stress the fact that, or remind you of the fact that if you start with a group of class 2, nilpotency class 2, then you get naturally a bilinear map alternating from the commutators. Okay, this is just because your commutators are central. This is a very easy exercise. So what we want to do is reverse engineer this. So construct a group, P group of class 2 from a bilinear map. And how do you do this? Well, we can start from any field. I'm going to take characteristic P different from 2, but you can sort of tweak this construction also over characteristic 2. And in my applications, the field will be finite. So I'm writing it between brackets just because this is where I want to go later. We start with 2 vector spaces over our field, take dimension n and d. These will be sort of my recurring integers. And I take a bilinear alternating map from v times v into t. Okay? And this, since we're outside of characteristic 2, this is a skew-symmetric map. And today when I talk of a tensor, I will be meaning this. Okay? And how do I build a group? I just take as the underlying set, I take the direct sum of these 2 vector spaces, and then I tweak the operation on them using this t. Okay, so I'm essentially building a 2 cocycle out of my tensor and taking the extension of v by t with this new cooked up cocycle. Okay, so let's see some examples. Some properties first. If k is finite, then we can say a number of things. So we can control the order, right? My vector spaces had dimension n and d, so the order is the size of the field to the n plus d. Unless my tensor was trivial, so sending everything to 0, the group will have class 2. And all the commutators of my group will be contained in the second vector space, T. And of course, if I fix bases of my two vector spaces, I can describe my tensor as a matrix of linear forms. Okay? And the nice thing is that if I start with P, my prime being different from 2, then every group of class 2 and exponent P can be described this way. Okay, so this is a very natural way to go back and forth. Okay? All right, so some examples. As I said, if we have the 0 tensor, then we get an abelian group, and this is not very interesting. If my matrix B looks like this, so I have one unique indeterminate, and then I have a skew symmetric matrix that looks like this, then what I get as a group is the Heisenberg group of the field. If this is the B that I start from, the matrix of linear forms, then I recover precisely the example of Dussertot and von Lie, the one that I promised you I was going to explain how it was constructed. And I want to make some remarks around this example. So the first remark is that, so you see this matrix B is a skew symmetric matrix that comes in a block form. Yeah, the zeros are 3 by 3 zeros. The M is a 3 by 3 matrix that looks like what you see on the slide. And if you take the determinant of M and set it equal to 0, this defines an elliptic curve in the plane. Okay, so this is really coming with this Weierstrass equation you see there. And if you take the determinant of B, of course you get the square of the determinant of M. But this is in general a general fact that if you start with a skew symmetric matrix, you will get a square, and then the polynomial whose square is the determinant of your matrix is called the Pfaffian. Okay? And one thing that I also want to remark is that this M is symmetric. Okay? This is a particular thing that you can observe, and that will come back later. All right? So when they produced this example, they showed that this counting function was not PORC of the automorphisms, but the way they computed the size of the automorphism group was not really suggestive towards generalization. So it wasn't really, it was clear that this elliptic curve was playing a role, but it wasn't clear how. So with Christopher Fall, when I was a postdoc at Bielefeld, we figured out what was really playing a role, and we managed to give a closed formula for the size of this automorphism group. Okay, and you can see it here, and I'm gonna comment on all of these pieces. So this size of this Galois group comes into play if you work over a finite field that is not necessarily the prime field. So they didn't have this part because they were working with groups of order p to the 9 only. This factor here, this is the number of 3 torsion points of the elliptic curve. Yeah, I reminded you at the beginning that elliptic curves come with a structure of an abelian group, so it makes sense to talk of their 3 torsion. We're over finite fields. This is a finite number divided in 9. Okay, and the reason why the 3 torsion points play a role will be clear in a moment, but you can think of these also as the flex points of your curve. And this is really what gives a non-PORC contribution. This GCD here counts the number of automorphisms of your curve as an elliptic curve, so preserving the group structure. And this other factor here, the GL2, comes from the fact that the matrix M that I showed you before was symmetric. Okay, and then there's also a correcting factor that comes from the central automorphisms. Those we always have, they're not so interesting. All right, so to prove this theorem, we did look at a theorem of Hesse that gave us 3 by 3 symmetric determinantal representations of elliptic curves. So we managed to generalize this specific example also to elliptic curves with J invariant 1728. And I should also mention that to prove this theorem, we also really figure out the structure of this automorphism group. It's just a bit complicated to write out, but there's more in the proof than it is in the statement. Okay, so how do we go from here? So we saw there was this elliptic curve, there was this non-PORC behavior. What else can we say if we want to generalize what was done in that example? Well, first of all, let me say I want to consider isomorphism for these groups that I told you on, these class 2 exponent P groups, but I want to do it for base field, the prime field. Just because the statements are easier, but you can also do it for any finite field. It's just that here, what you do for groups is the same as what you do for the Lie algebras. All right, so this is a known folklore, say, result at this point. It's if you want to test isomorphism between groups of this type, it's the same as finding matrices X and Z, such that you get this relationship between the two matrices of linear forms. If you want to see it in a less in a base-free way, what you're doing, you're constructing a pseudo-isometry between your two tensors. So if you see your maps, if you see your tensors as bilinear maps, what you're doing, you're finding linear isomorphisms of the vector spaces that make the diagram commute. Okay? And one of the consequences of this theorem that I showed you is that the isotropic behavior of the two maps is the same. So it means that we have a correspondence between the isotropic subspaces with respect to the first bilinear map and the second one. Okay, so all the information is preserved, and this is good because, for instance, if we have a matrix in block form like earlier, then also the other one will have up to this equivalence a form like that. Okay? Another consequence of this theorem is more geometrical. So I showed you in the example you could take the determinant of your matrix of linear forms. Yeah, this determinant could be 0, and then you get no information. But if it's not 0, okay, then it will the Pfaffian will be a homogeneous polynomial of degree half of the size of your matrix. Okay, and if that is the case, then you will have a naturally associated variety that is defined by taking the 0 points of this Pfaffian. And the consequence is that if my two groups are isomorphic, then the varieties associated to the Pfaffians will be linearly isomorphic. So now I'm finally ready to tell you why the 3 torsion points play a role in the non-porcness and in the formula I showed you before. And that's because if your Pfaffians define elliptic curves, then you will have to have a linear isomorphism between the two curves. And up to tweaking, you can really restrict it to linear automorphisms of the curve. And these are described precisely by products of isogenies of the curve composed with elements, with translations by 3 torsion points. This is everything you can have. So this is how these guys come into play. Okay? So this is that. We spoke of Pfaffians, but actually we have more structure. So we don't only can take the determinant of the matrix, we can take rank loci. Okay, and so instead of saying I take only the determinant of the big matrix, I fix a rank, I take the rank locus, and I consider the projective variety associated to the rank ideal. Once I fixed the size of the minors I want to consider. And then I get the same statement. Yeah, the varieties associated to the rank that I picked, they have to be linearly isomorphic. So one thing that you can deduce from here is that there are geometric invariants that are immediately associated to your group, to its isomorphism class. And though we have some invariants that really come from algebraic geometry, so dimension, degree, number of irreducible components. Over finite fields, we have more because we can count. So also counting rational points here is really, really powerful for us. Okay, it is difficult sometimes to really count how many things you have, but this is something that you cannot oversee. Okay, so it's extra information that we gain from working over finite fields. And as a snapshot, I told you I was going to talk mostly about elliptic curves, but I also wanted to tell you quickly, only on one slide, about something that we did recently with Damon O'Brien, and it has to deal with these invariants. So I'm focusing only on exponent P class 2 groups, okay? So one thing you can do is you check if I have 4 generator groups with commutator subgroup of order P to the 3, so I have groups of order P to the 7. If I look class 2 exponent P, I only have 6 groups up to isomorphism. These are classified. But you can check that you can test isomorphism here with only 2 invariants. We wanted to see how far off we were with these invariants. We wanted to use them as non-isomorphism testing, but it actually turns out you can do more. Well, they're quite effective in certain cases. We moved away from this case, looked at n equal 5 and d equal to 3, so I still have the commutator subgroup of size p to the 3. And here there are 22 groups up to isomorphism. We can tell them all apart except for a pair. This is still open, I can tell you more about this if you like later, but this is also quite nice that we managed to do this. And we can increase the size of the groups. So now we keep the n fixed, but we increase the size of the commutator subgroup. And in this case, there's 57 groups, and we can tell them all apart with invariants. Of course, I'm saying, we checked in computation, you have to P37. One could sit down and do all the properly, see whether it works theoretically, but we did this with magma up to P equal to 37. And if we increase further the size of the commutator subgroup, well, this is the first case in which we don't have a constant number of groups anymore of exponent P and class 2. The number of them changes according to the prime. So here I wrote the number of isomorphism types if I fix P equal to 5. And by just running experiments, we managed to construct 60 different invariant vectors. So it's still a pretty good result, I think. Maybe we can push it further, but so far so good. At some point we had to stop. By this I mean, of course, if you have different vectors, they tell you the groups are not isomorphic, but you could have isomorphic groups with the same vectors, right? So here we have bins in which we put our isomorphism classes, but these bins are larger than the isomorphism, their isomorphism class. Okay, so this was just, I just wanted to comment quickly on these invariants. If you have questions, just please interrupt me. All right, so I showed you what happened for these small values of n and d, and I went as far as I could with n equal to 5 because of duality. There was the largest size, let's say, of the commutator subgroup that I could achieve. But if I fix d equal to 3 to be small and let the n be larger, then the next sort of natural case is to look at n equal to 6 and d equal to 3. Yeah, n is the number of generators, and d is the dimension, let's say, of the commutator subgroup. And in this case, there is no classification available of these groups, but what happens is that generically what we know is that the Pfaffian of a matrix, 6 by 6 matrix of linear forms in 3 variables will generically define an elliptic curve. So it really makes sense to look at these guys, because most of them will be of this form. Okay? And here's the first theorem that we proved together with Josh, and it has to do with the first consequence I told you about with the isotropic subspaces. If we start with a group GBK, I call it elliptic if the Pfaffian set equal to 0 defines an elliptic curve, and we're in the n equals 6, d equal to 3 case, then the number of isotropic subspaces of dimension 3 that we get is 0, 1, 2, or size of the field plus 1. These are the only possibilities, and they all occur. And the interesting thing is that if any of these two, if I pick any of these two, they will always intersect trivially. So a piece of comment on this before I finish stating the theorem is that the zero case does not occur over fields of algebraically closed fields. So this is really something that is specific to finite fields. This can happen. So this is already something that takes us apart from the algebraic geometry that we can use. Okay, this is a separate case that we have to address. The 2 case corresponds to when we have a matrix that is decomposed as the ones that we saw before, but the M cannot be symmetric. If the M is symmetric, then we get many more of these isotropic subspaces. Okay, so we have this classification of the cases, but the nicest thing is that we can test in which case we are in polynomial time. And this can be done by computing something that is called the adjoint algebra of the tensor. This is an object is defined like this. What we test is the isomorphism type as star algebras. These were classified in a paper of Brooksbank and Wilson. So we know exactly what types we can get from their paper, and these are objects that are computable in polynomial time. So I can tell you in which case we are, and in polynomial time, and with Josh we focus on the, let's say, red and blue case. So when the matrix is decomposable, in this sense, with the big chunk, with blocks of zeros. And now, if we are in this case, then we can sort of simplify a little bit isomorphism testing in the sense that 2 groups will be isomorphic if and only if now we can check the isomorphism on the smaller matrices, on the 3 by 3 instead of the 6 by 6. But now I have to find 3 matrices that allow me to change the matrix from the 2 sides and from the linear part inside. All right, so I am in this decomposable case and I know I can do this. And now I draw from the literature. And I call for a very difficult theorem of Bourville that though ensures that the 3 by 3 determinantal representations of the elliptic of a given elliptic curve are parametrized by its rational points minus the point at infinity up to some sort of equivalence, and the equivalence, sorry, I keep forgetting this, the equivalence is very similar to the one on the top, but it does not allow me to linearly change the coordinates. So I can only operate on the outside. Okay, the reason why I wrote Hesse in pink is that if you specialize to the symmetric determinantal representations, this precisely corresponds to taking the 2 torsion points minus the point of infinity, so precisely the points that have order 2. And you have, over the algebraic closure, precisely 3 of them. Okay, so you can have at most, up to this equivalence, at most 3 symmetric determinantal representations. And this is something that we also found in the literature, luckily, a very explicit description of this correspondence from a paper of Ishizuka that tells us how to give these determinantal representations once we start from a Weierstrass equation and a point. This is how you prescribe the determinantal representation from your given point. And what I want you to note is that if you take mu equal to 0, this means that you're precisely taking a point of order 2. And if you set mu equal to 0 there, you see that you get a symmetric representation. You get a symmetric matrix. So if we go back to the examples that we saw before, the elliptic curve of Dussault and Folly was this one, given in Weierstrass equation, and the point was the 0, 0. And if you want to build the other 2 symmetric ones, the 2 points are plus or minus 1, 0. Okay, so let's put everything together now. I told you that if I give you a 6 by 6 matrix of linear forms in 3 variables that describes an elliptic curve, I can, in a polynomial time, check whether my matrix is decomposable, and then thanks to the theorem that we just saw, I can associate to it a pair EP, so the curve and a point. Okay, the curve will be unique up to isomorphism, but the point might not be. Okay, so you still have to deal with this problem. And here's our theorem, first theorem, that says that if P is at least 5, then given these two groups associated to, curve E, pair E and P, and pair E prime and P prime, then these will be isomorphic if and only if there exists an isogeny of elliptic curves, so an isomorphism of projective varieties mapping E to E prime, sending the 0 of E to the 0 of E prime, and also mapping P to P prime. Okay, so you can think of this as an isomorphism of curves with 2 marked points. But we're really relying on the fact that we have Weierstrass equations, so it's a bit tricky to talk in these terms, but this is essentially what is happening. And thanks to this, one thing that I should mention before I tell you about this theorem is that this can be now done in constant time, because we know precisely what the isogenies are between elliptic curves. We know exactly what they look like. There's at most 24 of them. For P at least 5, there is at most 6 of them. So it's really constant time, very quick. This is great. Yeah, we did all the work before to finally be done with something extremely quick to check. And thanks to this theorem, we're also able to compute the size of the automorphism group of such an elliptic group. And you see it resembles a bit the formula that we saw before. So this is the size of the stabilizer of P in the automorphism group of the curve. We still have the 3 torsion points, and now we have a distinction whether we're in the case in which the matrix M was symmetric or not. So we now have a full description of this. And now I want to tell you something about, and also, sorry, I should mention that these theorems are simplified, because I told you I just wanted to talk about the case where K is equal to FP, but we also have formulas and results for when K is any finite field. You just have to add a twist by Galois. So it's trickier, but it can be done. And according to consequences, so what can we do now? Everything I showed you is implemented, and we determine computational costs for performing isomorphism testing of these elliptic groups. So we know we can check so I have 2 given groups, so for P to the 9m, otherwise it doesn't make sense, because they have to be a 9th power of a size of the field. We can decide whether these 2 groups are of the shape we know how to deal with, and there's many field operations, and we can perform isomorphism testing and provide the collection of the isomorphism between these 2, and there's many field operations. So you see that being able to control the structure really gives advantages in terms of computational costs for performing isomorphism testing. So this was the first part of my subtitle, isomorphism testing. I have a second consequence that deals with the PORC conjecture, and I had promised you that I would, at the end of the talk, try to convince you that the example that we saw with the elliptic curve and the non-porkness was not very special. And why is that? Well, I gave you the automorphism, the description of the size of the automorphism group of these groups, and we saw that again, the only factor that could play a non-PORC role is the size of the 3 torsion points of the elliptic curve. Okay, so the question is now, when does it happen that it's a non-PORC function or not? Okay, so say I start to talk about varying over the primes. I start over Q, okay, and then I reduce modulo the primes. There will be some bad primes, but those we leave out. And Feynman's abelian polynomial theorem tells us that this function ensures that this function will be quasi-polynomial or PORC if and only if the Galois group that I get by adjoining all the 3 torsion points over Q is abelian. Okay, so I have a way of testing when this function is quasi-polynomial or not. And I ask, okay, when does this happen that this is abelian? Okay, this is just a translation. Well, there's a result of Duke that tells us that this basically never happens. So you have to order your elliptic curves, and we do this by height. This is a quite standard way of ordering the elliptic curves. And then the result of Duke is that the density of these curves, according to this, to the height of the curves for which the Galois group is abelian, is 0. So this tells you, in other terms, if you want to pick an example that is similar to the one we saw at the beginning, you'll more certainly get it by randomly picking. Otherwise, you have to look hard for those that will have an abelian behavior, so a quasi-polynomial behavior. If you want to do this, here is a piece of information. There is a paper of Bandini and Palladino where they precisely classify all the cases in which this Galois group is abelian. So you want a special example, you look here and you cook up your group the way I told you. Now you have all the information that you need. And I think I'm done. So this is my last slide. Here are the papers that I spoke about. So the one at the top is the one with Josh, and I also wanted to include the ones that I told you something extra about, and the implementations of the algorithms, so both for the elliptic curves but also for the invariants that I told you about. They are online, so you can access them and check them. Thank you.